Now we discuss next lecture, lecture number 2, solution of the 2024 question paper SEC-3 numerical in chemistry. The question paper, question 2, what do you mean by fixed point representation? Why is it convenient in most cases? Or question 2b, derive the equations for the coefficient a and b if the equation y equal to ax plus b is to be fitted to the set of points xi, yi. And this question, um, fixed point representation, already we have discussed in the previous video. So we have got this discussion at this moment. And the next question, or question 2b, derive the equation for the coefficients a and b if the equation y equal to ax plus b is to be fitted to the set of points xi, yi. The equations for the coefficients a and b, linear equation y equal to x plus b fitted to set of points xi, yi are given data, bivariate data, are derived using the method of least squares. The goal is to minimize the sum of squares of vertical distances, residuals, between the observed yi values and the predicted y cap I equal to axi plus b. Actually, this y is the observed value and this y cap is the predicted value by this equal to a plus xi plus b, vertical distance of the residuals. This is the x-axis, is the y-axis, and y equal to ax plus b. This is the line y equal to x plus b, and say this is the observed value. This is a xi comma yi. So this is the distance xi, say x1, x2, and this is the distance, corresponding distance height is this, corresponding yi. So yi cap equal to the predicted value of this axi plus b. So this is this height from this point to this point. This is the yi cap predicted value on this. So this is the observed data. This is x1, x2. This is the observed data. This is the observed data, and we want to fit a straight line y equal to ax plus b within this help of this observed data. So this is the error. This is the vertical distance. This is the error, and actually we want to minimize this the residual. This is the y minus axi minus b whole square. The distance square. We want to sum of these distances square is to minimize. This is the method of least square. This is the hence the name is method of least square. The objective of the function is to minimize this yi minus yi cap whole square. Actually, this is the yi is the observed data, and this is the yi cap calculated from this axi plus b. This is the predicted data. This is the we want to minimize this yi minus yi cap whole square, and this is the vertical distance. We want to minimize this is the distance yi cap minus yi. This is the distance is this whole square, summation of all vertical distances. We want to minimize this. Hence the name is method of least square. To find the minimum of S, actually here the variable S is a variable, two variables A and B. So by the knowledge of analysis, if we want to minimize this function S, which is a variable, which is a function of A and B, so we want to uh, calculate del B of S, partial derivative with respect to B, and del A of S. These two partial derivatives is set to equal to 0, is set to 0. And then for this 0, this del will be of S, derivative of this 2 into of this minus 2 into with respect to B. So this 2 into this with respect to this B, so minus B is minus 1 here. With respect to A, 2 into this is this minus, here xi is constant, yi is constant here. When S is a variable of A and B. So setting the derivatives to 0 yields a system of two linear equations known as the normal equations. Del B of S equal to 0. This after simplification we get summation yi, I runs from 1 to n, minus a summation xi, I runs from 1 to n, minus n into b, because there are n data here. And del A is equal to 0, gives this summation xi yi, I runs from 1 to n, minus a summation xi square, minus b summation xi equal to 0. These two equations known as the normal equations for this y equal to ax plus b, fitting this straight line y equal to ax plus b. Solving these two normal equations, we get b equal to summation yi cap by minus by n minus a into summation xi cap by xi by n. Actually, this summation yi by n is y bar, is arithmetic mean of y, minus a into x bar, arithmetic mean of x. Substituting this expression for b into the second normal equation, if we put the value of b in the second equation, normal equation, this, and after simplification, we get this, a equal to this. Hence, the formula for the slope a, actually y equal to ax plus b. So we know that y equal to mx plus b. This y equal to mx plus b, mx plus say mx plus b or a. So this m gives the slope. So this slope is this angle theta, so tan theta gives this slope. So here a equal to actually is the slope of the um, straight line, and b is the y-intercept of this. We get the value of a equal to this, and after in the formula of the slope is this. After simplification, we can write this summation bracket xi minus x bar into bracket yi minus y bar to summation xi minus x bar whole square. And the formula for b is b equal to y bar minus ax bar, and x bar is the mean, arithmetic mean, and y bar is this arithmetic mean of x and y respectively. Question 3a, consider the values of x0, f0, x1, f1, x2, f2, and so on with arbitrary spaced xi, obtain Lagrange's polynomial for the above set of data. The Lagrange's polynomial for a set of points n plus 1 arbitrarily spaced data points, and this is given by the formula px. This px, this is approximately Lagrange's polynomial. This is equal to summation fj lj. J runs from 1 to n. Lj are known as the Lagrange's basis polynomials, which is defined by Lj x, this is the pi, capital pi, I equal to 0 to n, I not equal to j, x minus xi whole divided by xj minus xi. Actually, this is the form. This Lj, actually this Lj form is this x minus x1, x minus x2, x minus xn, x0 minus x1 into x0 minus x2, x0 minus xn. This is the L0 into f0 plus L1 is this x minus x0, x minus x2. Notice that this x minus x1 is omitted. X minus xn whole divided by x1 minus x0, x1 minus x2. But x1 minus x1 is not permitted here because this is the 0 denominator. X1 minus xn. So this is the L1x into f1. So this L0x, this into f0, this L1x into f1, this lnx into fn. This is the Lagrange's basis polynomial of this. This is the pi. Pi means the product of these terms when I not equal to 0. To construct the Lagrange polynomial Px of degree at most n that passes exactly through each given data points. Here data points is this x0, f0, x1, f1, x2, f2, and a given data points. So we want to fit a polynomial. Actually here we don't know the exact polynomial. We want to approximate polynomial, this Lagrange's polynomial Px. Lxj is the Lagrange's basis polynomial. This Lj equal to xk 1 if j equal to k, and this j not equal to k, this is equal to 0. So this is the pxj, this Lagrange's polynomial is exact the value of the functional value fj for the data point x0, x1, x2, xn. And so this is the Lj xk. So L1 x1 is 1, L2 x2 is 1, and but L1 x2 is 0. This property guarantees that when we form the sum px equals to this, evaluating px at any specific point xk yields the correct function of fk. So this pxk equal to, put here the point xk in place of x, so we get this. But L0xk, this 0 by the definition of this Ljxk equal to 1 if j equal to k, this is equal to 0 if j not equal to k. So only here Lkxk is equal to 1. So we get Pxk equal to fk. Hence this Pxk equal to fk. So we get this expansion, the Lagrange's interpolating polynomial Px equal to, this is the formula for Lagrange's interpolating polynomial. Next question, graphically explain the second order Runge-Kutta method. There are two-stage Runge-Kutta method, RK2. One is modified Euler's method, other is improved Euler method, Hens method or Hans method. Here we discuss the modified Euler method. Already we have discussed this modified Euler method in the previous video for this geometrical representation. So this formula, actually this is the formula k1 equal to h f xi yi bar. Actually yi bar is the computed value of y, and yi is the exact value of y, and this k2 equal to this. Actually this is the modified Euler method. Actually is the midpoint method, also known as here the given initial condition x0 equal to y0, and this is the curve, exact curve yx, not fxy. Actually dy dx equal to fxy is the slope of this curve. This fxy represents the slope of the curve is y equal to yx, curve is y equal to yx. So we draw this tangent at the point a. This is the tangent. Next, we draw the midpoint of the tangent segment. This is the x1. X1 is this, and this draw. Actually, this tangent M. Actually, this tangent is parallel to the exact curve yx at this point, intersecting point of this. So already we have discussed this. So next question, question 4a. What is trapezoidal rule? Give a geometrical interpretation of the rule. Trapezoidal rule is the numerical integration method used to approximate the definite integral of the form a to b integration a to b fx dx. And this is the in subintervals with the step length h, a to b fx dx. This is approximately equal to h by 2 bracket fx0 plus 2 into fx1 plus fx2 plus fxn minus 1 bracket close plus fxn. So this is the x1, x0 is a, and xn is equal to b. In the subintervals, this x1, x2, x3, and xn, this endpoints, this a and b, and this is the construct with a trapezium here. This is the point, length height is y0, this height is y1. The exact curve, the red curve, is the y equal to fx. But this numerical integration, approximate numerical integration by trapezoidal method, we construct a trapezium on this each subinterval, on the each subinterval. So next we calculate the area of these subintervals and sum of these all areas of this trapezium. The each subinterval forms a right trapezoid, where the x-axis is the base, the vertical height at the functional value fxi and fxi plus 1. This is the corresponding y0, actually fx0, and this height is y1, that is fx1, this height, corresponding height in violet color. And the width of the interval, step length is h, serves as the trapezoid's altitude, the trapezoid's height, actually this h is the step length. So area of one trapezoid is the h by 2, height by 2, and this uh, sum of the two parallel sides. This is the these are the parallel sides. So this y0 plus y1 into bracket into h by 2. This is the formula. So area of the trapezium, half of the sum of the parallel sides into height, and we sum all of this trapezium, we get the approximate numerical integration of this a to b fx dx. This is up to the question 4. Thank you.